A warm welcome to part 4 of the lecture on functions. In the previous lecture, towards the end, we looked at a classification of functions based on the nature of its domain and codomain. We looked at things like a real valued function, a complex valued function, vector valued functions, functions of a single real variable, several real variables, etc. In this lecture, we will try to understand some other concepts like the notion of one-to-one functions, many-to-one functions, surjective functions, bijective functions. And finally, we will wind up with the notion of the inverse of a bijective function. So let's start. Let f be a function from a to b. It is said to be a 1-1 or injective function if distinct points in the domain A map onto distinct points in the codomain B. In other words, if f of x1 is equal to f of x2, then this must imply that x1 is equal to x2 if f happens to be a 1-1 function. A 1-1 function is also called an injective function. As a visual aid, you can see from this figure that the first example is that of an injective function because, as you can see, each distinct point in the domain A is getting mapped to distinct points in the codomain B. On the contrary, the other example is that of a many-to-one function. A many-to-one function is one which is not 1-1, which is not injective, because there are 2 points in the domain A which have a common image. Let us see some examples. A trivial example of an injective function is the identity function fx equal to x for all x belonging to R. You can verify it very easily. As another example, consider fx equal to 2x plus 3 for all x belonging to R. To check whether this function is injective or not, let's see if we equate f of x1 with f of x2. So if f of x1 equals f of x2, that implies 2x1 plus 3 is equal to 2x2 plus 3, which implies x1 is equal to x2. Thus the function is injective. As I had already pointed out, a function which is not one-to-one is said to be a many-to-one function. This means that there are at least 2 distinct points in the domain F such that they have a common image. There are 2 distinct points x1 and x2 belonging to the domain of F such that f of x1 is equal to f of x2. A trivial example is f of x equal to c, which is the constant function. Why is that? Because every point x in the domain maps to the same point c. Let's see some other examples. Fx equal to x square where x belongs to R. F of minus 2 happens to be equal to f of 2. Thus, this is also an example of a many-to-one function because 2 distinct points minus 2 and plus 2 have the same image 4. Similarly, the function sin x from 0, pi closed interval to R is an example of a many-to-one function because f of pi by 6 is equal to f of 5 pi by 6 equal to 1 by 2. Sine 30 degree is equal to sine 150 degree. At this point, let me make a very important remark. The property of injectivity depends strongly on the domain of the function and not just the correspondence rule. Which means for the same correspondence rule, 2 functions may be such that one is injective and the other is not. For example, consider the function f from R to R such that f of x is equal to x square. We have just seen that this function is many-to-one because f of minus 2 is equal to f of 2. However, the function f from semi-closed interval 0, infinity to R such that f of x is equal to x square is a one-to-one or injective function. This is because our domain is now restricted to the set of all non-negative numbers as opposed to all real numbers as in the previous case. For example, if we consider the number 4, there is exactly one number which is 2 whose square is equal to 4. The other number -2 does not lie in our domain. Therefore, for this particular function with the restricted domain equal to the semi-closed interval 0, infinity, this function happens to be actually a 1, function. Similarly, the function sine from the closed interval 0, pi to r is a many-to-one function because sine 30 degree is equal to sine 150 degree. However, if we restrict the domain to 0, pi by 2, closed interval 0, pi by 2, the function sine x becomes a 1-to-1 function. Now we address the following question. Is it possible to determine from the plot of the graph of a function whether it is a 1-1 or a many-to-one function? The answer is yes, and the procedure is as follows. If every straight line parallel to the x-axis intersects the graph in at most one point, then the function is injective. Otherwise, the function is not injective, it is many-to-one, which means that there exists a horizontal line which intersects the graph in at least 2 points. Let us see some examples. Consider the function f from r to r, fx equal to x square, which is the standard parabola. Now this is a horizontal line which intersects this graph at 2 points, as you can see. So it's a many-to-one function, as we have already seen. Consider the identity function y equal to x. Any straight line parallel to the x-axis will intersect the graph in at most one point, in fact exactly 1 point. So this is an example of a 1-to-1 function. Sine function from the closed interval 0, pi to r has the following graph, and as you can see there is a horizontal line which intersects the graph at 2 distinct points. So this is an example of a many-to-one function. On the other hand, the same function restricted to the closed interval 0, pi by 2 is a 1-to-one function because any straight line parallel to the x-axis intersects the graph in at most 1 point. Similarly, it should now not be difficult to understand why the function fx equal to x square, where x belongs to the semi-closed interval 0, infinity, is a 1-1 function, because any straight line parallel to x-axis is going to intersect the graph in at most 1 point. Let us now define an onto function. A function f from a to b is said to be an onto or surjective function if range of f is equal to its codomain b. We have seen many examples of functions whose range is not equal to its codomain. Those functions are not surjective functions. For a function to be surjective, its range must equal its codomain, which means for a function f to be an onto function, every point in the codomain must be an image of some point in the domain. That is, for every y belonging to b, there must exist at least one x belonging to a such that f of x is equal to y. The following figures will illustrate the concept efficiently. The first example is that of an onto function, and in fact also 1-1, because every distinct point in A is getting mapped to distinct points in B. And moreover, every point in B is the image of some point in A. The other example is also that of an onto function because every point in the codomain set B is the image of some point in the domain A. However, this is not an example of a 1-1 function because two distinct points are getting mapped to the same image. This is an example where the function f is neither 1-1 nor onto. It's not onto because There is a point in the codomain set, namely this point, which is not the image of any point in the domain. And also these 2 points have a common image, which is this point. Therefore, this function is also not 1, 1. The last example is that of a function which is 1, 1 but not onto because of obvious reasons. This is a point in the codomain which is not the image of any point in the domain A. We now proceed to make 2 important remarks regarding the onto function. The first one is the following. The onto property depends not just upon the correspondence rule but also upon the codomain of the function. For example, consider the function sine from R to minus 1, 1 closed interval. This is an onto function because for every y belonging to the closed interval minus 1, 1, there is a point in the set of real numbers whose image is the point y. Alternatively, in this case, the range of the sine function is same as its codomain. So, we can conclude that this function sin x from R to closed interval minus 1, 1 is an onto function. However, the function sin x from R to R is not onto because in this case the codomain set is the whole set R, which is not equal to the range of the sine function. You can also argue like this. Consider the number 2 belonging to R. There is no real number x such that sin x is equal to 2. So there is a point in the codomain which is not the image of any point in the domain. Therefore, this function sin x from R to R is not an example of an onto function. Now we come to the second important remark. The domain of the function also plays a crucial role in determining whether the function is onto or not. In other words, for the same correspondence rule and the codomain, there can exist 2 functions, one of which is onto and the other is not, depending upon their respective domains. Let us illustrate this by means of an example. Consider a function f1 from the closed interval minus pi by 2, pi by 2 to minus 1, 1 closed interval, such that f1 of x is equal to sin x. This is an example of an onto function because the range of f1 is same as its codomain. Now consider another function f2 from 0, pi by 2 to minus 1, 1, both closed intervals, such that f2 of x is also equal to sin x. So we are basically keeping the correspondence rule as well as the codomain same. However, f2 is not an onto function because minus 1 by 2, for example, is not the image of any point in the domain which is closed interval 0, pi by 2. So the conclusion is, despite the fact that the correspondence rule as well as the codomain are same for functions f1 and f2, while f1 is onto, f2 is not. We now define what is meant by a bijective function. A function which is both 1, 1 and onto is called a bijective function. Some easy examples are the identity function, x maps to x, the sine function from the closed interval minus pi by 2, pi by 2 to the closed interval minus 1, 1, the tan function from the open interval minus pi by 2, pi by 2 to r, the exponential function from r to open interval 0, infinity, the logarithmic function from the open interval 0, infinity to r. All these are examples of bijective functions because, as you can verify, these functions are both 1, 1 as well as onto. Associated with the bijective function is a very important concept, that of the inverse. Let f from a to b be a bijective function. The inverse of f, denoted by f inverse, is a function from B to A. That is, for the inverse function, the codomain B becomes the domain and the domain of f, which is A, becomes the codomain, such that f inverse of fx is equal to x for all x belonging to A. So f inverse is a function from B to A which maps the point f of x to x. Let us understand this visually. So f is a bijective function from A to B which maps the point x to the point f of x. Then the inverse of f will be a function from B to A such that the point f of x in B will be mapped to the point x. So basically the inverse maps the image of a point x to x itself. Let us consider the inverse of some familiar bijective functions. The inverse of the identity function is the identity function itself, as you can verify. For the logarithmic function from 0, infinity to r, the inverse of the logarithmic function is the exponential function, because exponential of log x is equal to x.